So the next speaker is Professor Francisco Planes, and he is principal investigator at the University of Navarra in Spain, focusing on the development of algorithms for molecular network analysis in cancer and personalized nutrition. And he will talk about the science underneath the iDiet app. So, yes.
Okay. Okay, sorry. Atrás, ¿cómo es esto? Okay. 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 One more. Okay. Thank you very much, Darius. I'm going to talk about the algorithm to rank food according to gut microbiota. Sorry. Our starting point is that the human gut microbiota degrades input dietary compounds into key microbial metabolites that regulate host health. We have metabolites that are health promoters, and we have metabolites that are disease promoters. That's our starting point. The question is, can we control through diet the production of these key output microbial metabolites, considering that each individual has a different gut microbiota composition? That was our question. How to control the production of these key output microbial metabolites. But the previous fundamental requirement and scientific question is that if we know how input dietary compounds are degraded into key output microbial metabolites, can we model how these input dietary compounds are degraded into these output microbial metabolites? So to answer this question, our approach was to rely on metabolic networks. At that time, it has been released in Nature Biotech, an impressive repository of metabolic reconstruction of almost 800 members of microorganisms of the human gut microbiota, developed by the group of Ines Thiele, and the repository is called Agora, and it can be extracted from this webpage. Networks integrate thousands of reactions that occurs in different microorganisms, and they are stored in different databases. We're going to work with this one, okay? With these networks, we can build microbial community models where different species can be treated as a different compartments. And what is most important, with these networks, we can connect input dietary compounds with output microbial metabolites, okay? It's similar to logistic network, to city networks, but here we have reaction network where the nodes or the city are metabolites. I'm not going to put any mathematical formula, but what is even more interesting is that this community model can be contextualized for different individuals using metagenomic data. In our case, 16S RNA gene sequencing data taken from stool samples. Okay, so depending on the microorganism you have in the microbiota, you're going to have a different metabolic capabilities. Okay. In addition, in this community model, we can contextualize the different foods we are taking, because different foods has different input compounds here, and again, we're going to have a different output microbial metabolites. We're going to have a different metabolic capabilities. So to build these context-specific or personalized community models, we integrate different data from different partners in Stance4Health. For 16S RNA sequencing data, we have here Pilar, and also all the information about food with the different databases generated in the consortium, also with the help with Professor José Ángel Rufián and iDiet. So we have all the ingredients to build these personalized microbial community models. Our work was to, once we have all this data, take all this data and predict for different foods the automicrobial metabolites that are going to be synthesized, okay? And we start to do this work, but we found that in Agora, in this repository, was the information about key input dietary compounds was insufficient. It was difficult to connect the information we have with e-diets with Agora, because many degradation pathways for these nutrients was not annotated. So we developed a different complex bioinformatics and computation pipelines to complete these networks that was more amenable to integrate with e-diets. We validate with different datasets and different nutrient families that we were more accurate than Agora to predict the output microbial metabolites using targeted metabolomics data, but also uses untargeted metabolomics data, and with very different compounds, nutrient families. So now this was an important milestone in the project. We have the human, a more accurate human metabolic network of the gut microbiota. But the question is still there. How Agreda, our repository, our human metabolic network is called Agreda. It's an improvement of Agora. So Agreda accurately defines how input dietary compounds are degraded, but the question is still there. How can we use Agreda to personalize the diet and rank food for its patients? So we follow this strategy. We select a number of target metabolites based on literature and metabolomics data. Some of them were healthy and some of them were unhealthy, okay? That was our first step. Define this list of automicrobial metabolites we want to target, okay? We want 42 metabolites we want to follow, and they are going to give us the state of the human, of the gut microbiota. And then, using our computational approach, using the metagenomics data and Agreda, we run foods according to a global scale that considers the capacity to produce more of healthy target metabolites and less of unhealthy target metabolites. Here we have 4 metabolites, okay? And we analyze for each individual the capacity to produce more of the healthy, here these are healthy, short-chain fatty acids, and one here is unhealthy. And we construct a normalized integrated score for the capacity of different foods for different individuals to produce these metabolites. This is interesting to note that this curve here was built using a reference distribution from healthy individuals taken from a completely different cohort, okay? So somehow we can give a normalized score, considering healthy individuals, of the capacity of the different foods to produce more of the different target metabolites. Here, we have here 4 foods, okay? 4 different samples. Obviously, we can find some of the foods that are always, in general, are good for the microbiota. And we also have other foods that are general bad for the microbiota. This is Spanish chorizo. Okay. This is broad beans. I took a lot of broad beans in the lunch. This is a secret. but also the interesting thing was this one, this chestnuts, that for some individuals are very good, and for some individuals are not that good. And this is very dependent on the gut microbiota. Okay, possibly these individuals lack some particular microorganisms that are making a much better use of these different foods. Okay, this approach was applied to all the samples and different interventions we have in the project. Yes, as a final conclusions, using Agreda, metagenomic data and food databases, we have built a novel ranking algorithm, food ranking algorithm for each individual according to gut microbiota. This is something very unique in the scientific literature. The second point is that the definition of target metabolite is a central decision in our approach that can be adapted to specific clinical conditions. And this is something we can continue improving for different versions of the app. Because perhaps for diabetes patients, we have a different panel of biomarkers, of metabolite biomarkers. We are also now conducting additional experimental validation to demonstrate this ranking of food using in vitro fermentation experiments that were generated in Stance4Health. And as I just told, we have also integrated our microbiota-based food score with iDiet software in order to provide individual nutritional recommendation in human intervention. So thank you very much for all the team at Technion, my PhD student, Telmo and Francesco are in the framework of this project, has conducted their PhD studies. And thank you, the Commission and all the partners of Stance4Health. Thank you very much.
Thank you. We have 5 minutes for questions.
Slido.
Yes. Is this? Are these from before? Yes. I thought, wow, that was quick.
Veronica, come here. Okay.
Yes. So maybe the most important question for some is Agreda open source somewhere?
The Human Metabolic Network, Agreda, is open source and is published in Nature Communication, so it's already available since 2021. What is not available is the ranking algorithm. We're still deciding what to do. Possibly we want to protect it, or
yes.
But yes, the Agreda is open. It's open source.
If Anonymous was interested in, if they could get access to the algorithm, what is that something in the future?
I have to. I cannot answer this question right now, but we are also studying if we're going to publish the algorithm. We are going to explode it. We are in that discussion. So yes. Currently we haven't the algorithm available for the public, or really available, obviously.
Yes. Other questions? Yes, in the back. We'll get you a microphone.
Need to find my way first here through.
Yeah, thank you for a very nice presentation, and also the very interesting information you have got from assembling all this data. But I was wondering, Of course, everybody is using fecal samples to monitor the microbiota by metagenomics. But I was wondering, don't we miss something? Because the digestion of food, of course, is happening in the small intestine. And what we see in the fecal samples, of course, is not resembling the small intestinal microflora. Of course, it's very difficult or even not possible to sample the small intestine. But I was wondering, aren't we missing important information by just focusing on fecal samples and so what's happening in the large intestine, the colon?
Yeah, I agree. This could be an additional improvement in our algorithm to not only take in consideration the microbiota, but also considering that these outputs could be also degraded in the intestine by intestinal cells and produce another and get to the blood with another transformation that could be mediated. But in the project, we have to, as Pilar says, we also have boundaries in the project, and we decided to stop and validate with the gut microbiota. That's, I agree with you. We could improve the outcome of the algorithm by considering also the metabolic contribution of intestinal cells. For example, one additional limitation of our algorithm we are currently working and we are improving is that at the moment in the algorithms we use the microbiota composition as something static. Okay, you have a photograph of your microbiota when you take the sample, but this is something very dynamic, and you have also interactions, nutrient interaction with bacteria. And we have created a new version of the algorithm considering this dynamic interaction between bacteria and nutrient. And this is something, in many cases, we have interactions that are not metabolic, but also regulatory. And this is something very interesting. But yes, we have many ways to improve and hopefully we have the opportunity to keep improving our approach in the future.
Next we have questions from the online audience, and one from Stephanie Bodenbach asking if the screenshot sample recipes refer to, for example, Serrano ham. Do you advertise geographic indication covered foods in the app? Is this appropriate for EU-funded project? I'm not sure if this goes to the algorithm itself, or if you can speak to that.
Yeah, I think we have.
But if not now, maybe this question will be answered then after the conference. And the next one also goes
for sure,
more to the app. So, well, thank you, Professor Francisco Planes.